Hi guys, in this video we're going to take a look at conditional events, calculating conditional probability formulae, examples, and then we'll finish with a summary.
So what exactly are conditional events? When dealing with independent events, specific emphasis is placed on the fact that the events do not affect each other. Let's say that on the first toss of a coin we get a head, and on the second toss of the coin we get a tail. These two events are independent because they do not affect each other in terms of their outcomes. Similarly, let's say we have two collections with replacement of a counter from a bag. Let's say that the first one comes out as a red and the second one comes out as a blue. Similarly, because they are with replacement, these two events do not affect each other and hence are independent. However, in reality, outcomes of previous events often change the probabilities we would like to consider. Let's say that previously there's been a period of higher temperature, and then we have the event going from cloudy to going to raining with our weather, or let's say we had a period of lower temperature, and then our weather going from cloudy to going to snowing is another event. We can see that the temperature that we previously had affected the probability of having rain or snow afterwards. The temperature affects the weather, and hence those two events are not independent. It is useful to be able to describe an event's likelihood based on the outcomes of other events. Let's say we have the first pick of a counter and it's a blue. Or we could have the first pick of a counter and it was red. We'd like to know that in the two cases we take this forward, what is the chance of the second pick being specifically blue? We can do this by seeing which outcomes an event depends on and then calculating conditional probabilities. So how exactly do we calculate conditional probability? The probabilities of events that are affected by new information are called conditional probabilities. A conditional probability is a probability that takes into account information. For example, suppose we pick two counters without replacement, one after the other, from a bag containing 3 red and 2 blue counters. We're looking to take one, our first counter, and then not replace it into the bag, and then take a second counter. The probability that the second counter is blue is conditional on the outcome of the first pick. If our first pick is red, then for our second pick we have available 2 out of 4 blues to pick from the total number of counters. If, however, our first pick is blue, then we have only 1 blue from a total of 4 counters to pick. Therefore, for our second pick, the probability of picking a blue counter is 1/2, but in the second case, the probability of picking a blue counter is instead only 1/4. It's conditional on the outcome of the first pick. The probability that an event B occurs, given that an event A has already occurred, is written as the following. We write the probability of the event B, and then we draw a line, and that means given event A has occurred. Again, this straight line means the word given. Similarly, the probability of B occurring given that A has not occurred is written as the following. The probability of event B given that A has not occurred, and so we write A complement. When calculating the probability of B given A, we only care about the outcomes which are already found in event A. If we have our Venn diagram with events A, B, and our sample space C, now we only care about the events in A because event A has already happened when we're calculating the probability of B given A. We can form a sample space from the outcomes found in event A, known as a restricted sample space. We have the event A as the big circle, and we're going to consider the whole of event A as our restricted sample space. Within our restricted sample space, when we're looking at the probability of B given A, we'd like to consider the event B intersection A, those that happen when both A and B happens, i.e. in particular, all outcomes in B which are also in A. The event we wish to find the probability of in our new restricted sample space consists of all the outcomes in B found also in A. As a result, the probability of the event B, if we know A has occurred, can be found by dividing the probability of both B and A occurring by the probability of A occurring. This is because we're dealing with our restricted sample space, and we'd like to know the ratio of the probability of the outcomes being in here over the outcomes being in the whole of A. So we get that the probability of the event B given A is equal to the probability of the event B intersection A divided by the probability of specifically the event A, due to the description we gave above. For example, consider the situation used above. We're looking to take two counters from this bag, but specifically without replacement. Suppose that A is the event that a red counter is picked first, and B is the event that a blue counter is picked second. We have that the probability of blue second, given that red happens first on the first pick, is the probability, by our definition of A and B, of the event B given A. By our formula, this is the probability of B intersection A divided by the probability of the event A. Let's consider the probability that red occurs first and blue occurs second. This, by our definition of A and B, is the probability of A intersected with B, because and is the same as an intersection. But by symmetry, this is the same as the probability of the event B intersection A, because we can write them in the opposite order and it still is the same. So looking for the probability that we have red first and a blue second, we're looking to remove specifically a red on the first pick, and therefore by looking at how many reds we have and how many blues we have, the probability of this occurring is 3/5, and we're looking to take a blue on the second, again this is with replacement, so now we only have 2 blues and 2 reds. Probability of taking a blue is going to be 2/4, which is equal to 1/2, and we're looking for the probability of these both occurring. Now that we've done this in this exact way, these two events will be independent. This is because we've specifically considered one individual case, and therefore we can calculate the probability of blue occurring second, given that red occurs first. Again, the formula is the probability of B intersected with A divided by the probability of the event A occurring, and by independence, the probability of B intersected with A is just these two probabilities, 3/5 and 1/2 multiplied together. So we have 3/5 multiplied by 1/2 as our numerator, and our denominator is the probability of A occurring, and A is the event that a red counter is picked specifically first, and therefore this is also going to be 3/5 because we considered that above. This was our first case, a red counter being picked first. And therefore these cancel out and we get specifically 1/2 as our final answer. So what other conditional probability formulae do we have? We have just met the formula for conditional probabilities. We have the probability of B given the event A is equal to the probability of B intersected with A divided by the probability of the event A occurring. Now sometimes it is helpful to use the rearranged version of the formula. That is that the probability of A intersection B, which by the way is the same as the probability of B intersection A, by multiplying up is the same as the probability of B intersected with A multiplied by the probability of A. For example, note that by symmetry we have two equalities for the intersections. We have our first one, which is that the probability of A intersection B, precisely by writing out the formula as above, is equal to the probability of B given the event A multiplied by the probability of the event A. But also, by swapping around, we have that the probability of A now, given B, is going to be the probability of A intersected with B divided by the probability of B, just by swapping the events A and B. And when we multiply, this gives us, again, the probability of A intersected with B is equal to the probability of, this time in the opposite order, A given B multiplied by the probability of the event B. Equating the two above equalities gives another useful formula. Because the probability of A intersected with B is equal to the probability of A intersected with B trivially, we can equate the right-hand sides, and therefore we get that the probability of A intersected with B multiplied by the probability of the event B is equal to the probability of B given the event A multiplied by the probability of A. This formula helps us directly relate the probability of an event A given an event B to the probability of B given A. Let's say we have two events, event A and event B. And event A is the event that it is cloudy at 11 o'clock, and event B is that it rains at 12 o'clock. Then by our above formula, we have that the probability of cloudy at 11, given that it rains at 12, multiplied by the probability that it rains at 12, is equal to the probability that it rains at 12, given that it's cloudy at 11, multiplied by the probability that it's cloudy at 11. This means that if we have three of these probabilities, then we can work out the fourth. Or at least if we can calculate three of these probabilities, we can calculate the fourth. If two events A and B are independent, then they should not affect each other. Let's say that we know that events A and B are independent. Then we would expect that the probability of, say, A given B is equal to the probability of event A given not B, i.e. B complement. We should expect this should occur just by thinking about what this says. The probability of A happening given that B happens must be equal to the probability that A happens given that B does not happen, i.e. B happening or not has no impact on A happening. We would expect that the probability of A occurs given B has occurred is the same as if B had not occurred. For independent events, the multiplication law simplifies the conditional probability formula. Events A and B are independent, and by definition that means that the probability of A intersection B is equal to the product of the probability of A multiplied by the probability of B. And therefore, if we consider the probability of specifically the event B given that A has occurred, this, by the formula we had before, is equal to the probability of B intersection A, or by rearranging A intersection B, just by symmetry, divided by the probability of A. But by using our independence multiplication formula, the top is the probability of A multiplied by the probability of B. And since the bottom is also the probability of A, this will cancel out from the top and the bottom, and we just get the probability of B, i.e. the probability of B given A is just the probability of B. A has no effect. A similar thing occurs for the probability of the event A given B, as well as the probability of A given not B complement, as well as finally the probability of B given that A complement occurs. They are all purely equal to their first component, i.e. the first one is just the probability of A, the second one is also the probability of A, and the third one is just the probability of B. The second, i.e. the given event, has no effect due to independence. This allows us to find a new independence condition, i.e. A and B are independent if the following occurs. The probability of event A given event B is equal to the probability of event A given that B does not occur B complement, which is also equal to the probability of A. This is because if this equality holds, B has no effect on A, and therefore A and B are independent. Similarly, we can reverse this and have that the probability of B given the event A is equal to the probability of B given the event A complement, which is also equal to the probability of B. Again, for the same reason, if this is true, then we have independence between A and B. For example, in the case that the counters in the bag above are removed with replacement, events A and B become independent. And again, to check independence, we need not verify all of these equalities. We only need to verify that, say, the probability of A given B is equal to the probability of A. We need not consider all 6 and make sure that they have their respective equalities. One of them will suffice. So we have that the probability of the events A given B, and we defined A and B before, is equal to the probability of A. And similarly, by reversing, we have that the probability of B given event A is equal to the probability of B. The only difference here is that we have with replacement rather than without replacement. We're considering the second pick occurring after the first pick, and we're considering the situation where the contents of the bag reset for the second pick. E.g., after the first pick occurs, we replace whatever count we get back into the bag, and we have the same contents as we had for the first pick as we then have for the second. Let's take a look at some examples. Our first example says that the probability that a randomly chosen person living in the UK has lung cancer is 1 over 1,000. The probability that the randomly chosen person smokes is 1/6. Only 1 in 2,000 both smoke and have lung cancer. What is the probability of a randomly chosen individual having lung cancer given that they smoke? This is an important probability to be able to calculate in dealing with medical issues such as these. Our first step is to recall the formula for conditional probabilities. The probability of event B given event A is equal to, by the formula, the probability of B intersected with A divided by the probability of A. Our second step is to define the required events. Let's let event A be the event that the person smokes. And the event B, let's let this be the event that the person has lung cancer. Our third step is to calculate the required probability. We'd like to find the probability that the person has lung cancer given that they smoke. This is the probability of, by our definition of our events, B given A. By our formula, this is the probability of B intersected with A divided by the probability of A. And now we can use our information in the question. The probability of B and A is the probability of having lung cancer and smoke, which is 1 in 2,000. So that's 1 over 2,000. And the probability of A is the probability that they smoke. So that's 1 in 6. And by dividing, this is 3 divided by 1,000, or as a decimal, 0.003. So we can see that smoking has an effect on the probability of having lung cancer. The two events are not independent. Our second example tells us that during the summer there is a 4/5 chance that it will be sunny in the afternoon on any given day. There is also a 1/2 chance that James will bring his sunglasses with him for the afternoon on any given summer's day. If the probability that James brings his sunglasses given it is sunny in the afternoon is 5/12, find the probability that it is sunny in the afternoon on a day when James brings his sunglasses. Lots of words, but all we need to do is to interpret them. Our first step is to recall the formula relating the conditional probabilities of the two events. We have the probability of A given the event B multiplied by the probability of the event B is equal to the reverse, i.e. the probability of B given A multiplied by the probability of A. Our second step is to define the required events. Let's let A be the event that it is sunny in the afternoon, which I'll denote as sunny. Again, we should be specific, but I'm just going to annotate it as sunny. And B be the event that James brings his sunglasses on that given afternoon, but I'll just write that as sunglasses. Our third step is to write down the probabilities of the specified events. All we have to do here is to interpret the question. We have that the probability of the event A is equal to, let's have a look at the question, 4/5. That is the probability of it being sunny. We have the probability of B, and looking at the question, this is going to be precisely 1/2. This is the sunglasses probability. And then finally, we also have the probability of the event B given A. This is the last remaining number in the question, which is 5/12, because this is the probability of sunglasses given that it's sunny, so B given A. And this is again 5/12. Our fourth step is to rearrange the formula to write the required probability in terms of probabilities we know. We have that the probability of A given B, which is the one we want to find, is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. Our last step is to calculate the required probability. We have that the probability of, let's have a look, we're looking for sunny given sunglasses, that's sunny given that he brings his sunglasses. By our definition of the events A and B, this is equal to the probability of A given B, and by using our above formula and the values that we found, this is equal to the probability of B given A, which is 5/12, multiplied by the probability of A, which is 4/5, divided by the probability of B, which is 1/2. And therefore, this ends up as being 2/3, and that is our final answer. Our last example says that given probability of A is 0.2, the probability of A and B is 0.1, the probability of A union B is 0.6, we're asked to find both the probability of B and the probability of B given A, and then by considering these two probabilities, comment on the relationship between the events A and B. Our first step is to recall the union intersection formula. We have that the probability of the union A union B is equal to the probability of the event A plus the probability of the event B minus the probability of the event A intersection B. Our second step is to calculate the probability of B using this formula. By rearranging, we get that the probability of B is equal to the probability of the union, A union B, minus the probability of A plus the probability of A intersection B. And therefore, by using the values in the question, the probability of A union B is 0.6, the probability of A is 0.2, the probability of A intersection B is 0.1, and when we add and subtract, we're going to get 0.5. Our third step is to recall the formula for conditional probabilities. We have that the probability of B, given that the event A occurs, is equal to the probability of B intersection A divided by the probability of A. Our fourth step is to calculate the probability of B given A. By using our results above in the question, the probability of B intersected with A we have as 0.1 because by symmetry the probability of A intersection B is equal to the probability of B intersection A. And then we divide by the probability of A, well that is 0.2. So by dividing we get 0.5. Our last step is to compare the probabilities, probability of B and probability of B given A, and form a conclusion about the events A and B. We have that the probability of B is equal to 0.5, as above, but that's also equal to the probability of B given A, and again, both equal to 0.5. This means that we can deduce that because A has no effect, i.e. the probability of B is equal to the probability of B given A, that A and B, the events A and B, are independent. This is the relationship between the events A and B.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together, let's make A-level maths a walk in the park.